Welcome to the Rich Report, a podcast with news and information on high-performance computing. Today, my guest is from MathWorks. We have Silvina Grad-Frelich, and Silvina is the Senior Manager of Parallel Computing at MathWorks. So, welcome to the show, Silvina.
Hello, how are you?
Oh, terrific. I'm glad you could be with us today. And I have your slides up here on the screen, so why don't we start with that?
Great. Thank you very much for inviting us to participate at your podcast. So the goal for our conversation is to discuss a new announcement. The announcement is that Lund University, one of the leading research universities, used MathWorks tools to improve the long-term survival rates for heart transplants. The university researchers explored complex relationship between multiple transplant variables, including weight, gender, age, and analyzing these variables usually requires thousands of simulations that are exploded to thousands of patients. Usually these thousands of simulations took weeks using open source software that is also unstable and inaccurate. So to address all these challenges, researchers use MathWorks tools to develop artificial neural network models to simulate these thousands of combinations using a computer cluster. The results that we'll see, and we'll come back to this use case later during the presentation, is that the model showed that the matches that are found with this software are 5 to 10% higher than the matches that are usually used by physicians today. And not just that, but also that the simulation time was cut from several weeks to a few days. One interesting detail that I want you to keep in mind is that this application was programmed by Dr. Nilsson, who is a physician, not a programmer. He was able to use a cluster from MATLAB without having to be expert in programming, and more importantly, without having to be an expert in parallel programming or having to learn any other programming languages. So let's see how he did it. So before we get into the details, I would like to introduce MathWorks and other of the concepts that I mentioned in our first slide. So MathWorks is the leading developer of mathematical computing software. Engineers and scientists worldwide rely on products that the MathWorks produces to innovate. MathWorks products are used through automotive, aerospace, communication, electronic industries as fundamental tools for research and development. They are also increasingly used in other industries such as financial services and computational biology. More than 5,000 colleges and universities around the world are also using our tools for teaching and research. So many of you are familiar with MATLAB, which is our first core product. MATLAB is the leading environment for technical computing, and it's also the foundation for all other MathWorks products. MATLAB is a programming environment for algorithm development, data analysis, visualization, and numeric computation. The other core product is called Simulink, which is a leading environment for modeling, simulation, and implementing dynamic and embedded systems. Simulink is the foundation for model-based design. Now, I presented the two core products. In addition to MATLAB and Simulink, the company produces more than 100 additional products for specialized tasks such as data analysis and image processing. So now that we have introduced MathWorks and the two core products, I would like to introduce our parallel computing tools that were used at Lund University to speed the applications that they build using MATLAB and the Neural Networks Toolbox. The Parallel Computing Toolbox is an add-on to MATLAB. It's a set of functions and libraries and APIs that allows users to extend MATLAB. It allows MATLAB users to program parallel applications in their desktop computers. These parallel applications will be able to speed up by taking advantage of the desktop CPUs and GPUs. For many of our customers, we have seen that the speed that they get using their desktops is good enough. for some other users, they need additional performance, so they may need to scale their applications to clusters, grids, or clouds. So in this case, we have another product that is called the MATLAB Distributed Computing Server, which runs on a backend. When I mention the backend can be a cluster, a grid like the Terra grid, or a cloud such as Amazon EC2. The interesting fact is that the same parallel application that was developed by a user in their desktop can scale to a larger environment without doing any additional code changes. So we'll spend the next few slides trying to understand why this is the case, why they can program a parallel application and scale to whatever environment without doing code changes. So a key concept that is important in program parallel applications and parallel MATLAB applications is called MATLAB Pool. A MATLAB Pool is a collection of workers where a worker is basically a MATLAB session that is running somewhere. And that place can be a desktop, a cluster, the cloud. A MATLAB application or a parallel MATLAB application will run against this MATLAB pool, this set of workers, independently of where the workers are running. So when we talk about doing parallel computing with MATLAB, we are talking about addressing two main types of problems. One is speeding up computations. And basically, this is the type of problems that is called task parallel problems. In general, these are computations that take a long time to run and can use additional resources to run these tasks in parallel. The key of these task parallel applications are that the tasks are independent one from the other. The second type of problem is what is called the data parallel problem. And these problems involve dealing with very large data that cannot fit in a desktop computer or in a single machine. And in contrast to the task parallel applications, this type of problem require sharing data across multiple machines. So for both type of problems, we have solutions that are provided by MathWorks parallel computing tools. For this presentation, we'll focus on the first one, that is speeding up computations. Now, when in general you want to parallelize an application, there is a trade-off that you need to do. You can either try to get the last bit of performance out of your application, which will require a lot of control and changes in your application, or on the other side, or the other extreme, is to do as little changes as possible and get the performance improving while still maintaining your attention in the problem instead of trying to solve just the parallel aspect of it or just to get speed. The majority of the customers that we have talked, of our customer base, namely engineers and scientists, prefer the second option. They want to continue investing in their research and engineering tasks instead of becoming parallel computing experts. So this relates very much to an interview that you did in November of 2010 with Steve Wallach, the founder of Convex Computer, where he was saying that MATLAB basically is the easiest to use and the most productive HPC language. And what he was referring is that people can stay in their domain while having access to all these HPC hardware that is available, as opposed to program just the nuances of their parallel program. So you can solve the value proposition of these products, of the parallel computing products with MATLAB, is that you can solve problems doing easy or minimal code changes to your application. So some of the solution is by already implementing parallel algorithms by ourselves, by MathWorks, in our own tools called toolboxes or block sets. So let me explain a little bit in more details what that means. What that means is MathWorks has already used parallel computing tool to parallelize some of our most time-consuming functions in our product line. This list shows a sample list of toolboxes and block sets that have improved their algorithm performance relying on parallel computing tools. And here at the bottom of the slide, you have a link to a web page where we have the complete list of all the toolboxes and block sets, add-ons to MATLAB and Simulink that are speeding up already by using the parallel computing toolbox. The key is that a user that uses these functions, for example, in the communication toolbox or optimization toolbox, doesn't need to make any changes to their code to speed up using the underlying infrastructure. Now, what happens if the compute-intensive part of the application is not in a toolbox that we provide, but in your code, in the code of the engineer or scientist? So for that, we do provide high-level programming constructs that allow the user to parallelize their application by making very small code changes. So if we go back to one of the two kind of problems that we presented in an earlier slide, we see that many of our customers want to speed up compute-intensive applications made out of independent tasks or iterations. And one of the key concepts here is that there are no dependencies or communication between the different tasks. Good examples that are very prominent in the industry is parameter sweeps and Monte Carlo simulations. So for that, MathWorks has introduced a new keyword in the MATLAB language that is called par-for or parallel for loop. A par-for will take an existing loop and transform it into something that can run in a group of MATLAB sessions. So here is a piece of MATLAB code, which is not very important, but the important piece is that this pink box shows a compute-intensive part in the application that I developed, which is a calculation within a for loop. And here you have the for loop. So to parallelize it, you need to replace the for loop with a par-for. So here you have on the left the serial code, on the right the parallel code. So what you can see is that the parallel for loop or the par-for is written in the same function as your serial code. And now MATLAB will automatically run the code inside the loop on a MATLAB pool or a serial or on a group of MATLAB workers that are running somewhere in the background. These additional MATLAB sessions can reside either in a cluster or even in your local machine, and that's the way that you make use of the cores in your own desktop. You can think about the MATLAB pool as being a bit like being able to connect from your Word document or from Excel to many different printers. So you can print in a low-res printer or you can print in a high-res printer, but the document doesn't change. So in that example, your document is your MATLAB code, and the printer is basically the MATLAB pool that is running in different printers. So with this example, you can see how easy it is to convert a Monte Carlo code or a parameter sweep into something that will run on a multi-core machine or in a compute cluster. So we presented as of now how you can use built-in parallel computing support within toolboxes and block sets, and also how there are high-level programming constructs in the previous case was par-for to take advantage of the underlying hardware that you have available. So in the last few releases, we have also include or release GPU support that is at the same level. To make use of your GPU, you can define an array as a GPU array that resides in the GPU, and they apply functions to that array that will do the math without being an expert in writing GPU code or CUDA code. if you want to go all the way down to the maximum level of control to achieve maximum performance, we also provide low-level programming constructs. For example, we have some people that are, for example, parallel computing researchers that use our MPI or message passing interface library. You can also write your own CUDA code or GPU code and then invoke that CUDA kernel from within MATLAB. So let me go back to our initial slide where we talk about Lund University developing an artificial neural network for matching between transplant donors and recipients. So basically what Dr. Nilsson did was to program an artificial neural network in MATLAB using MATLAB and the Neural Network Toolbox, and then parallelize his application using the Parallel Computing Toolbox. He scaled up his application from his desktop to a 56-core processor cluster without doing any additional changes to his code. Now, again, as I mentioned in the first slide, the key thing is that Dr. Nilsson is not a parallel programming expert. He's a physician that is doing his own research, and he didn't need to learn any new programming language or very complex parallel computing terminology or functionality to parallelize his code. Yet he did very good, he got very good performance improvement by using these tools. He cut his simulation time from weeks to a few days. Now, we talk about Lund University case or user story. We have many other stories many other applications that were developed by customers. Here you have a list that is out of our website with different stories coming from very different industries. Let me give you other examples. For example, we have the Argonne National Laboratory that developed a powertrain system using MathWorks tools, including parallel computing tools. We have a Max Planck Institute that in their research for cancer tools or cancer solutions, they try to reconstruct key protein complexes using MATLAB. They had low-res pictures of the protein, and they wanted to reconstruct the protein structure by running thousands and thousands of simulations. And again, the doctor that did the simulations, he had just changed a for loop for a par 4. Other examples are here available and are also available in our website. So with that, I finish my presentation, and I want to open the floor for questions.
Well, thank you, Silvina. So I have a question about the research at Lund University, right? So the goal, as I understand it, was to improve the long-term survival rates of these heart transplant patients, correct?
That's correct.
Okay, so what were they simulating? It says they built an artificial neural network. Were they just applying different variables to see which patients didn't survive, or how does that look?
So the idea, and I'm not the expert in the research field, as I understand the idea is you have 6 variables that can be combined, and those basically are good. Those variables are expected to give you a good match when they are put together between the donor and the recipient. So what usually the doctors do is they do that work manually. So they make the decision, 1 or 2 doctors get together and make the decision based on research that they have previously done. But the decision is done by a doctor. So the idea of this piece of software is to provide a better and automated solution to come up with, once there is an organ donor, given all the characteristics in these particular variables, is to find the best match in the list of people that are waiting to receive an organ.
I see. So there's an organ becomes available, and they find the best match in terms of the person that could have the longest survivability using that particular heart. Does that sound right?
Sorry, go ahead.
Yeah, is that how it would work? A doctor would pull this software up and go find the ideal recipient?
That's correct. Now, the interesting detail in this particular example is that what takes a long time is to train the artificial neural network. Once the network is trained, that means that the results are the combinations are in the system. The doctor doesn't need to have access to a big cluster of computers like the one that they were using in Lund University. The neural network is trained and is available in the desktop machine. So it doesn't take such a long calculation time. It's just a matching with particular criteria.
Sure. So Silvina, I really love this story because it says the result of this was up to a 10% increase in the survivability rates for up to 5 years or more for these patients. And I did my little math in my head, and with 50,000 patients, that's like 5,000 people that are going to live longer as a result of this research. That's terrific.
Yeah, and the interesting thing that we are seeing is that people are using MATLAB and parallel computing tools to enable real research. So the research that they are doing have a very clear impact in the science that they are developing on the engineering that they are doing.
So let's double click on that, Silvina. So if this doctor wanted to do this without MathWorks and achieve this kind of computation, would it have taken like a whole stream of grad students to write a bunch of MPI code? I mean, how would they do that in the conventional method?
So that's a great question. The short answer is yes, you're right. Usually, in previous years, before these kind of tools were available, people were hand coding their parallel algorithms, meaning they were including MPI calls in their algorithms. So there are several problems to that, and the most clear problem is that that's error prone. Writing MPI is basically very low-level programming. So you can make a lot of mistakes that are very hard to debug. So basically you will have the attention, instead of the attention being in the science, the graduate students will be programmers, will be programming low-level languages. So that's one of the things. And the second problem is once you change, if you program MPI, most likely when you change your cluster configuration or the architecture that you're running on, you will need to retune your application, in many cases rewrite the application. So that is very time-consuming and, again, error-prone.
Well, that's terrific. So, Silvina, kind of a wrap-up question here. Looking forward, you know, we're talking about exascale computing 8 or 10 years from now when there might be millions and millions of cores and threads. Is MathWorks looking forward to that so that it could provide that kind of compute power to the doctors and the people that aren't the hardcore programmers?
So it's a great question, and I can think about many ways to answer it, but let me start by first qualifying where our customers are coming from. So
Sure.
Generally speaking, we are saying our users are engineers and scientists that until a few years ago, they were using their own desktops. And sadly, they saw that their problems got bigger and bigger, either because they were too compute intensive or the data was too large. So at this point, they are making or creating their own clusters, maybe accessing a grid like the Terra grid in the US or the European grid, or accessing the cloud. At this point, they are not using thousands and thousands of cores. However, we'll see them growing. The problems will continue to grow, but still is not at the scope of the exascale. Our users are not the typical HPC users. These are engineers and scientists that now have access to what used to be called the HPC hardware.
Sure.
So while this is a trend that is very interesting and very important, it's not exactly what our customers are targeting today. However, we do have customers that when the MATLAB in the TerraGrid node was available, the one that Cornell put together, they definitely used the TerraGrid. So you see most of our customers are still in the low end of the HPC environment, having access to hundreds of cores, and you can see some cases in which we have customers that are accessing the highest end of the HPC spectrum.
Well, terrific. Well, Silvina, thank you very much for coming on the show today.
Thank you very much for the invitation. Looking forward for our next conversation.
Okay, sounds great. Okay, folks, that's it for the Rich Report. Stay tuned for more news and information on high-performance computing.